This video will help discuss the Earth's interior and discuss also the evidence we have for plate tectonics. Now, Earth's interior, you're pretty familiar with. We're going to go quickly through it though. This image on the left is a rough approximation of the relative sizes of our different layers of the Earth. However, although they show the crust as being kind of thick here, truly it is a lot thinner. It's more relative in size actually to the skin of an apple as compared to the flesh and interior of the apple. So it's very thin. And here is a piece of the pie cut out of the Earth to show you no longer relative sizes, but just to see clearly the information about each layer. The crust is very thin on top, as we mentioned, and we're going to discuss the crustal type soon. But beneath the crust is the mantle. It's the largest layer, and it's what we call plastic. Now, this is not the plastic you're used to dealing with. This is meaning it's not quite solid, and it's not quite liquid. It's something in between. It seems very solid, but it does flow slowly, like a few centimeters each year. It is the largest layer, as I said, and it has convection currents, meaning heated material rises towards the surface, flows along underneath the crust, and then sinks as it cools. So density, again, from Unit 1, density is causing movement in the mantle, which then causes movement of the crust. Beneath the mantle is the inner and outer core. They are both iron and nickel. They are both metal. They are both spinning. However, the outer core is liquid. The inner core is solid. The inner core is solid, even though it's really, really hot. It's actually hotter than the melting point of iron and nickel, but it's under so much pressure from the weight of the Earth on it. Literally, the weight of the world is on the inner core. It is no longer able to stay in a liquid form. It's forced into a more compact solid. The outer core being liquid, though, and spinning is very important, because once you get into physics, you discover that moving metal produces a magnetic field. So this spinning outer core produces the electromagnetic field, and this is what gives us our compass. We have a north pole and a south pole. Our compasses point north. We use them to navigate, and this magnetic field also protects us from the solar winds. Now, this magnetic field only happens if you have a liquid core that is spinning. Mars, for instance, is no longer liquid in the middle, so no longer has a magnetic field, so a compass would be utterly useless there. Same thing for the moon. Alright, next we're going to discuss the crust. When you look at the crust, there are two sections of it. Here in this closer-up image, you see the yellow and the gray. The yellow is the solid lithosphere. Lithos actually means rocky. So this is the rocky part of the crust, what we're standing on. Beneath that is actually a mixture of both crust and the upper mantle. It is called the asthenosphere. And this is slightly more fluid part of the crust, and it moves more freely. Now also, if you notice in this image, the left side, we've got this blue is meant to indicate the ocean. Beneath that is the crust, and then beneath that is the orange mantle. To the right, it's a thicker layer of this yellow, and you see the mountains. Beneath that, the gray, and below that, the mantle. These are two different crustal types. On the left is the oceanic crust, and on the right is the continental crust. The most obvious difference, of course, is that ocean crust is thinner, while continental crust is thicker. Oceanic crust is actually more dense, while continental crust is less dense. Oceanic crust, obviously from the name, includes the ocean floor and most islands. Continental crust, obviously, is the continents. Oceanic crust is a dark-colored rock called basalt, B-A-S-A-L-T. It's made of minerals that are high in iron and magnesium, so high metal content, which is why they are more dense, and is a dark-colored rock. This is easy to remember because basalt is salt like the ocean. Not that it actually has anything to do with salt, but that does help, a little way to remember it. Continental crust, though, is light-colored granite, which is made of the minerals feldspar and quartz. So it's relatively glassy. It is less dense. And so what happens is, occasionally in plate tectonics, of course the crust is moving, so sometimes the ocean crust crashes into the continental crust. When this happens, the more dense ocean crust is sucked under, it sort of loses the battle, is sucked under the continental crust and is destroyed. Meaning, of course, that the ocean crust never gets very old because it's constantly being recycled, being sucked down into the mantle again. So ocean crust tends to be made of younger rocks. Continental crust, since it's less dense, it keeps floating and so is never sucked under into the mantle. It's never destroyed. It's just broken up a bit. So it gets much older. Looking into Earth's interior, this is a very interesting set of graphs. At the top we have a pie, if you will, that shows you the crust, including the lithosphere, asthenosphere, the mantle, outer core, and inner core. On the right, it shows densities. Starting at the top, you see granitic continental crust 2.7, basaltic ocean crust is 3.0. So again, the ocean crust is more dense. The mantle, 3 to 5, outer core, 9 to 12, inner core, 12 to 13. So as depth increases, density is also increasing. Next, we have this graph here. These two graphs here. They show depth along the bottom from 0, meaning right at the crust. That's what these dotted lines line up to. This is to the crust. Bottom of the asthenosphere, top of the outer core, top of the inner core. So the top of the inner core, for instance, is a little over 5,000 kilometers deep. As you go deeper, look at what happens to the temperature. The temperature increases, gets much hotter. In fact, when you get to the bottom of the lithosphere, it's at 1,000 degrees Celsius already. So the temperature greatly increases as you get deeper. Pressure, this is in millions of atmospheres. 1 atmosphere is the amount of pressure you experience at sea level on Earth. It's the weight of the air pushing down on you. Your body is very used to that. And as you know, when you go into water, there's more pressure on your body depending upon how deep you go. Well, when you go deeper into the Earth, the weight of all that Earth on top of you causes a great deal of pressure. And once you get into the stiffer mantle, it's at 1 million atmospheres, meaning you experience 1,000,000 times more pressure down there than you do at Earth's surface. And when you get down to the center of the core, you're experiencing roughly 3.5 million times Earth's normal pressure. So as depth increases, pressure increases as well. Alright, now we're going to get into some evidence for plate tectonics. We discussed Wegener a bit. Wegener was a meteorologist, actually, who started looking at maps and noticing some interesting patterns. First, of course, you notice that the continents fit together. Anybody had noticed that. But Wegener started plotting out some interesting information. For instance, this gray is Glossopteris fossils. This is a plant. Now, this plant is found a little bit in South America, a little bit up here in India, Southern Africa, Antarctica, Australia. And if you look at these locations, it doesn't make any sense. A plant can't swim across the Atlantic Ocean or the Indian Ocean. It also is very unlikely to live in what we now think of as Antarctica. So, if you put them all together, what's neat is the Glossopteris lines up. We've got this pattern here. Now it starts to make more sense. We have a fossil of a plant that lived in one band, kind of in the south. At that time, it's probably a little further north than that. And it's sort of like a forest running across the land. This was a good climatic area for it, temperature-wise, so it fit there. It didn't have to swim across any oceans because the continents were together. Next thing is also the coal beds. Coals are signs of ancient swamps. It is actually formed from plant material that doesn't quite rot. It sinks to the bottom of a swamp and then is not exposed to oxygen, so it doesn't quite rot. It just builds up layer after layer and is compressed into coal. We find coal in Pennsylvania, down here in northern South America, a few places in Europe, northern Siberia, and over in Asia. But what's odd is few of these places are really where we think of for a swamp, especially northern Siberia. It's very cold there. Not really a swampy place. But when you put the continents together, we end up with swamps at the equator. Well, that makes a whole lot more sense. Glacial deposits. Glaciers, signs of old ice. Obviously that makes sense in Antarctica. Not so much covering all of India, or Australia, or all of South Africa, or Rio de Janeiro. Not really glacial areas, but again, when you put the continents together, as in this map, the glacial areas fit together somewhere near the South Pole. So the interpretation that Wegener came up with is that fossils, folded mountains, because you see them here, South America and Africa, the same rocks, two sides of the ocean, again, rocks don't swim, on different continents match. So the continents must have been attached sometime in the past and moved away since. Wegener was laughed at, though, because he couldn't come up with any force powerful enough to move South America away from Africa. This was not discovered until much later. This is more fossil evidence that Wegener and others did discover. It wasn't just this Glossopteris plant, it's also Lystrosaurus, Mesosaurus, Cygnognathus. And again, they only make sense when you put the continents together. Next, we have the location of earthquakes and volcanoes. Earthquakes are the green dots, volcanoes are the red triangles. Earthquakes are signs that rock is moving, one against the other. This image actually shows it very clearly. It's showing all the earthquake epicenters from 1963 to 1998. And if you notice, it tends to draw lines across the Earth. This outlines what we've come to call tectonic plates. The Earth's crust is broken into roughly 16 major plates. Like here's the African plate. This is the Cocos plate, Nazca plate, Caribbean plate. It's broken into pieces, and the edges are where the rocks rub up against each other, producing earthquakes. Volcanoes also happen in similar areas. Here we've got the Ring of Fire, and again, the location of these volcanoes match up with the locations of the volcanoes, with the earthquakes. So most volcanoes and earthquakes are along what we call plate boundaries, and they are part of how we know that those plate boundaries do truly exist. One of the good results of World War II was that submarines were going back and forth from the United States to Europe very frequently, and while they were doing so, they were gathering great map data from the ocean floor. One of the things that was determined from this data was the age of the rocks of the ocean floor. This map has gray for the land, like here's North America, there's South America, and the colors indicate the age of the ocean rock, at least those areas that have been well mapped. And if you notice across here, it's a very pretty rainbow. Blue, green, yellow, red, yellow, green, blue. And notice it repeats on each side. And it's red in the center of the oceans. And it gets older as it moves away from the oceans. See if you notice the rainbow here. Age, this is in millions of years. Red is 0 million years ago, born today. Green is 83.5 million years ago. Blue is 180 million years ago. So as you move across the rainbow, you get older. So what we noticed is that young rock is near the mid-ocean ridge. This mountain range, that's what this black is, down the middle of the ocean. And it's brand new young rock. Lava is literally coming up right now and filling it in, making brand new rock. As you move away, the rock gets older, which indicates that new igneous rock, meaning rock produced from lava, is being formed at the ridge, then moves away as newer rock forms at the ridge. Let's show this happening. Right. So it's just being pulled up here, and then as it moves to the side, it gets older and older. The second point of data that the submarines came across was magnetism. What you may not be aware of is that iron in magma, there is a good deal of iron in the magma, it is basaltic in the ocean, orients itself to the North Pole. So the crystals then become frozen, meaning they solidify when the rock cools, leaving a record of where the North Pole was when the rock was formed. The magnetic North Pole moves around through geologic time. Right now it's wandering its way through northern Canada. But if you go back a little while, it used to be down in Antarctica. Yes, you heard me, the North Pole used to be down in Antarctica. The planet didn't flip over, simply the magnetic field flipped. So, like right now, we're in what we call a normal magnetism, because we're here, so we call it normal, where the North Pole is in Canada. But if you go back, this white is an indication that those rocks were actually formed saying that the North Pole is in Antarctica. And it was there for a little while, and then it moved. Then before that, it was up in Canada. Then it was a long while in Antarctica. And it flips back and forth. Not incredibly regular, but this is the pattern. And then look over here at the mid-ocean ridge. The red is indicating lava coming up to the surface, producing new rock, which is, of course, normal magnetism, because right now, since it's being formed right now, it's pointing north to the North Pole in northern Canada. But notice thick gray, thin light, very thin gray, thick white, thick gray, thin light, very thin gray, thick light. It's perfectly symmetrical on the left side and the right. And it continues. Look at the patterns. It continues on both sides of the mid-ocean ridge. It's completely symmetrical. The interpretation is that on each side of the mid-ocean ridge, since there's a mirror image of magnetism, showing the rocks at each side of the mid-ocean ridge formed at the same time, but then moved away as new magma moved in and made new rocks. This is the true evidence for plate tectonics that proved that the continents were moving. For instance, we've got North America right here and Africa over here. They're moving apart from each other, and we've got evidence in the rocks of the ocean floor. This image shows it. You see, the pink comes up, and then as the two areas move away, they move apart and get older, but they still hold the record of where the North Pole was. And you end up with matching rainbows on each side of the mid-ocean ridge. They were originally the same, and then they move apart. Okay? And they drag whatever continent is sitting on it away with it. So that is the evidence for plate tectonics. In the next video, we'll talk about what the plate boundaries are and some more information.